right, we are going to move on to section 15.4, which is the chain rule. So we're going to look at our chain rule when we have one independent variable. That'll make sense what that means here in a second. And our chain rule with more than one, not than one, um, more than one independent variable. And we're going to look at making some tree diagrams to help us make sure that we get everything in place where we need when we are finding derivatives with the chain rule. So we're going to start how we've been starting a lot of these sections here in chapter 15. We're going to look back at what we know about the chain rule and how we used it in 251. So we use the chain rule to find the derivative of functions that we made by composition. So this is where we take two functions, we're plugging one into the other. So for example, we've got our sine function here, and we've got plugged into it t squared. So we took that quadratic function, we plugged it into our sine function, and when we take the derivative, we know we take the derivative of that outside function, which is that sine function, and then times the derivative of the inside function, which is our t squared. Okay, and when we've done this millions of times. So when we view this equation above slightly differently and think about it, okay, what if we pull apart this composition? And this is usually something we talk about like one or two times at the very beginning of when we do the chain rule. But this is going to be really helpful for us to understand what's happening when we're looking at this in three dimensions. So we're going to take this apart as two separate functions. We're going to have our first function be y equals sine of x. So just that plain old sine function. And then our second function being x equals t squared. So we can easily put these together because x is equal to t squared, and we would get sine of t squared, which is what we had up above. But what we want to look at is taking the derivative of this, and we want to get how y is changing when t changes. Well, to get to that, we have to see how y is changing with respect to x, and then how x is changing with respect to t. Maybe we'll write that under there, how y is changing with respect to x. So WRT, that is, with respect to. And that just means that that's the one that we control, that we can change. That's our independent variable. And then a second derivative we have here, this is how x is changing with respect to t. And again, so what this is telling us is dy dx, we know what that is. That's a derivative. That's the derivative of our function that's underlined in orange, and we know that that's cosine of x. And dx dt, we know what that is. That's derivative of our green underlined function here. And the derivative of that with respect to t, where t is our independent variable, is 2t. Now, this is a little bit funky right here because we don't usually, have our answers written in two variables. And our question, our overall question right here, was how is y changing with respect to t? So we need everything in terms of t. Well, right here, again, x is equal to t squared. So this is cosine of t squared times 2t. So this idea of sort of chaining together these two rates of change, that's how our chain rule works. And again, what's nice about this is that these dy, dt, dx, dt, these are rates of change, and we can, we technically can cancel that dx, we can cancel out that intermediate variable there, and that can get us to how our y is changing as we change time. So to think about this in three dimensions, we're going to look at an example here. So I'm going to think about this function here for a second. So we got our regular sort of surface that we have in three dimensions. So z is equal to x squared plus x times y. Then what we're going to say is that, okay, x and y are going to change with respect to t. And again, you can think about this as time. That's totally fine way to think about this. That t is some sort of external parameter like time, that it's starting at 0 and it's going to 2 pi or something like that, or it's going to 5 seconds. And x and y are dependent on time. So, okay, how do these all fit together? It was a little bit easier to see back here how to get from one thing to the other. So, from Y, we, need to plug in X, but to get to X, we've got to plug in something to T. So it was a really kind of simple path to get, you know, from T to Y or from Y to T. Here, we've got Z, and Z is a function of X, and it's a function of Y. But X is a function of T, and Y is a function of T. And what we've made right here, this is kind of a simple one, but this is called a tree diagram. And it's just a picture of how these variables work together. And we can think about how our variables are changing. And we found our partial derivatives, dz dx, and that was how z was changing in the x direction only when y was held constant. We also had found our partial derivative with respect to y. So again, that's how our z values are changing when we change y, but we keep x constant. But both x and y, they are a function of t, and they are changing as t changes. Now, a little bit of a notation thing here, and we'll kind of notice this, that we use that scripty d when a variable is a function of more than one variable. So like in this case, our variable z is a function of more than one variable, x and y. And we use regular d when a variable, say x or y, is a function of, sorry, my handwriting is really bad, of just one variable. Again, say t. Ooh, this is making me crazy right there. There we go. Bad handwriting. Okay. So what we want to find with this is we want to look at how z is changing. Oops, and we just have one single variable here, so already, nope, z goes on the top because that's our output, and t goes on the bottom because that's our input. So we want to look at how z is changing with respect to time. So x and y are changing with respect to time, z is changing with respect to x and y. So because everything's changing in that x and y is sort of that in the middle that's connecting z and time, or z and t, we can use that chain rule. So if we follow our branches here, so partial z, partial t, whoops, partial x, there we go, times dx dt, plus following our second branch over here, our y branch, partial of z with respect to y times dy dt. So again, even though we use just that different notation, the scripty d versus the regular d, that scripty d really just tells us that, hey, we've got a function that's in more than one variable. And that regular d just says, hey, we've got a function that's in one variable. These still do technically cancel out. So we get z, dz dt and dz dt, which is what we want. So each of these little individual derivatives, all of these we know how to find. And that's really what we have to put together. So we'll go back to this first blue one, the partial of z with respect to x. So that's looking at this function right here, and it's asking for our partial derivative with respect to x. So that's going to be 2x plus y. The second part of our multiplication there, our dx dt, That's talking about this function right here. That's saying what's the derivative of that function with respect to t. Let's get green here. And that's going to be negative sine of t. And then we'll put an innocuous plus in there. And then our dz dy, that's back up here again with our function z, or f of xy, and taking the partial derivative, which on this one we're just going to end up with x. Okay, and then our last one, dy dt, that is this guy here. That y is equal to sine of t, and I don't really want to write this in yellow, so maybe we'll write it in red, that is going to be cosine of t. So similarly to what we were doing in 2D right here, that we ended up with that derivative with respect to x times our derivative with respect to time, and then we had to replace our x with t, or that function of t. We're going to do the same thing here. Anything that is an x or a y, x or a y or an x, we're going to replace it with these relationships right here, because x is cosine of t and y is sine of t. So this is going to change our derivative to be 2 times cosine of t plus sine of t, and this does need parentheses around this, times negative sine of t, and then plus x is cosine of t, and then times cosine of t. Now the rest of this is just prettying this up a little bit, using the distributive property here, multiplying that negative sine of t by what's inside the parentheses here, so that we get negative 2 sine of t cosine of t, and then minus sine squared of t, and then plus cosine squared of t. And sadly, we're so close to having sine squared plus cosine squared, but we don't. And this is all we can do with this. But that tree diagram and keeping things separate helped us piece by piece make this derivative, and it tells us how z is changing along this path t. So the real question is, what are we actually doing here? What does this mean geometrically? So I've got a picture for us. Okay, and so what we're doing with this x equals cosine of t, y equals sine of t, is that we're restricting our domain. So this is a domain restriction. And so we're saying we're going to only look at our function here, our f of x y function, when we have x and y values that satisfy these two equations, that x is equal to cosine of t and y is equal to sine of t. Because normally the domain of this function right here is all real numbers. So what this is going to do is this is going to create a path along our surface. So you've probably already taken a look at the two pictures that we have here. This restriction right here is this picture right here in 2D. It's a circle with radius 1. It's the unit circle where x and y are the points, on here on the edge, and there's arrows on it. It's directional because t is going to change. T is going to go from maybe 0, like I said, 0 to 2 pi, or maybe it's going to go 0 to 10, or maybe it'll go negative 5 to 5. But the orientation that'll go here is counterclockwise because it is the unit circle. So what that's going to do is that's going to make a different path than what we're used to. So in our partial derivative section, we were looking at really specific paths. We have only looked at paths where we're parallel to the x-axis or parallel to the y-axis. That's not always the path that we want to walk along on our surface. Sometimes we want to walk along a different path. So this is going to give us that ability to say, okay, I want to define a different path. And I want to say, how is this function changing along that path? So I've got a picture of the 3D graph over here, but I want to look at our more dynamic shot. Ooh, I've got it flipped upside down. So here I've got that surface graphed, and then I've got our circle, our domain restriction graphed and projected up onto our surface. So how did I do that? Took me a little bit of thinking here. So if you look over on the left-hand side, way, way, way down at the bottom, here, I'll shake it down there at the bottom, you can see our z is equal to x squared plus xy. So that's our function, that's the surface that we're seeing. And then I selected a space curve. So this is one of our vector valued functions. And I plugged in x of t, I put cosine of t, y of t, put sine of t, and then z of t, I graph. So notice this is exactly our function x squared plus xy, but with cosine of t and sine of t in for x and y. So what that does is it takes that circle, takes that parameters that we have for x and y, and it projects it up onto our surface so we can see what that path is. So let me animate this. So because I've got a point marked on that path there. You can kind of see it, it's a little black dot. But if I animate it, this is going to start moving that point around, and you can see that you can view this as like this is a little hiker and they're walking around this circular path. If we look at it straight on, you can see it's a little bit funky, but there's our circle and how we've restricted our domain. And so we're thinking about, so if we stop it here at a point, we can look at a specific point on this path and say, moving forward, what's our rate of change? Are we going downhill? Are we going uphill? Is it really steep? Is it really flat? So we can look at that specific point and how it's changing going in the direction of our path. Whoa, forgot every time I do this, it flips that up and moves this. So here's our path projected onto the surface. So like I said, this is going to give us a way to look at different paths and figure out what's going on in that direction. So we could, find dz dt when t is pi over 2. So we found the derivative. We found it right back here. It's this crazy thing. But we can take and we can plug in pi over 2 into that. And cosine of pi over 2. Sorry, I'm looking back at my notes to make sure I don't miss any pieces. Cosine of pi over 2, or sine of pi over 2, then cosine squared of pi over 2. And this ends up being -1. So if we were sitting at time is pi over 2, which would be, if we're looking down at the xy plane, right, pi over 2 is going to be right there. It's telling us that as we're moving forward, we've got a slope of -1. So if we move forward, we would expect that we'd be moving downhill at that point and at a slope of -1. So as we move along that path for just at least a little bit, it's going to be moving downhill as we go forward. So it's the rate of change at that moment. All right, let's see. Okay, we did already say that. Again, making sure I'm looking at my notes, making sure we've got everything that we need. So quick definition. So this is what we exactly just did. We've got z is a differentiable function of x and y. So z is equal to some sort of f of x, y. And then x and y are some differentiable functions of t. So they're like some sort of u of t, and y might be some sort of v of t. They're some sort of function of t. And we want to find how z is changing as time changes. And so here's our definition. But again, what I really like to do is to draw those tree diagrams once I see what my variables are and how everything connects up. We'll do this here where we've got some more variables to show why that makes a little bit more sense. So we can extend this so that x and y can have be a function of more than one variable. They could be a function of, say, s and t. So we could have, z is some function of f of x, y, and x can be some function, maybe we'll call it u, and it's some function of s and t, and y is some function also of s and t. So again, what this does is just gives us more paths that we can take. So we may just want to define, more and different kinds of paths on our function, and that's what these things are doing. So let's take just a quick look of what this looks like when we do have more parameters. So we've got our z is equal to 2x minus y squared, but then x is a function of s and t. It's s times cosine of t, and y is equal to s squared times t squared. So I like to make that t diagram and say, okay, again, we've got sort of z here at the top, and it is a function of x and y. X is a function of s and t. Y is also a function of s and t, but we could have this where x is only a function of t or y is only a function of s. That is also a possibility. They don't always have to have both variables. So if we were looking at rates of change here, since z is a function of two variables, it gets that partial derivative with respect to x, or we could find that partial derivative with respect to y. And then x, it's going to have a partial derivative as s changes or a partial derivative as t changes. Same with y. Remember to change my variable here. So we can find the partial derivative of z with respect to s. And here, everything's going to be partials because everything is in terms of two variables. Oh, so fun. We only get to use that regular d when it's just in terms of one variable. So this is going to be our partial of z with respect to x times our partial of x with respect to s. So again, we're just following along our tree branches till we get to s. And we'll do the same. We'll follow along our y tree branches until we get to s. And we multiply when we're following along our tree branches, and we add together each of our tree branches so that we've gotten to every place down here where we have an S. And so again, the thing to keep in mind is when we're at this point, we can do this. We can find these partial derivatives of all of these little individual things. So we've got the partial of z with respect to x. So that's again referencing our 2xy minus y squared. So its derivative, its partial, whoops, let's not be the highlighter. Okay, so its partial is going to just be 2y, yep. And then we'll have, orange here, partial of x with respect to s. So again, that's talking about this function right here. And that partial, the partial derivative, the derivative of s is 1. We're going to treat that cosine of t like a constant. Okay. And I do like to put parentheses around everything because often we need them because we're going to have distributive properties. We don't in that first one, but we could. So it's good to have them. Oops. Well, we can underline with green. We can do that because dz dy, that's going to be, again, using our 2xy minus y squared. So that derivative is going to be 2x minus 2y. And then maybe we'll do blue here. So partial of y with respect to s. So again, that's referring to that function right there. Our y is equal to s squared t squared. And that partial is going to be 2s times t squared. So again, now we're sitting at a point where we've got a derivative and it's in terms of x and y and all sorts of fun stuff. And we want it just in terms of s and t. So all the places that we have x's and y's, we're going to replace them with our two parameters here. So we're going to have 2t squared s squared cosine of t. Replace that y with our s squared t squared. Then plus 2 times s cosine of t minus 2s squared t squared. And then times 2s t squared. And so again, we really have the answer right here, but we generally like to, at the very least, multiply out any distributive property that we have, and we just have a little one right here that we need to do. Oops, and I guess I put a equals there instead of a plus. So we get 4, and we'll have s squared t squared cosine of t, and then minus 4 s cubed t to the fourth. All right, let me double check. That's what I got on my notes. All right, whew. All right, why don't you try out on your own finding the partial of z with respect to t, and we'll take a look at that in class. Maybe that will be our first example that we do in class.